Welcome to Numerical Methods for Scientists and Engineers with Pseudocodes. Video 5. One-step methods, trapezoidal, midpoint, and modified Euler's methods. The trapezoidal rule is a numerical integration method that is often used for solving initial value problems. The method is a second-order method and can be thought of as a combination of the explicit Euler method and the implicit Euler method. The method improves on the accuracy of the estimates by averaging the slopes at both the beginning, xi, and end of the interval, xi plus 1. This method is particularly useful for difficult problems, or when better stability and accuracy are needed over long periods of time. The trapezoidal rule replaces the slope in the IVP with the arithmetic average of fxi plus 1yi and fxi plus 1yi plus 1, which is also an implicit method. The derivative term is discretized using the central difference formula with respect to the midpoint. To determine the order of accuracy, we integrate the initial value problem from xi to xi plus 1. Replacing the integral with the trapezoidal rule gives the following, from which we can identify the local truncation error to be third order. The slope at each step is taken as the average of those of explicit and implicit Euler schemes, which does follow more closely to the true slope. For nonlinear IVPs, root-finding methods such as fixed-point iteration or Newton-Raphson can be applied to solve the following nonlinear equation at every step. In the nonlinear case of fxy, the difference equation for the trapezoidal rule is linearized using the same procedure applied to the implicit Euler method. The current step for the linearized trapezoidal rule is found to be, which allows the numerical estimates to be obtained recursively and explicitly. Notice that this expression retains the third-order local error as well as second-order global accuracy. The advantages of the method are: the trapezoidal rule is a stable implicit method. It has a second-order global error. A linearized scheme with a suitable H can be successfully employed to solve nonlinear initial value problems. The method suffers from the same drawbacks as the implicit Euler's method, i.e., since it is implicit, obtaining the current step estimate for nonlinear IVPs requires the solution of nonlinear algebraic equations, which increases the CPU time. In the midpoint rule, the first-order IVP is evaluated at the midpoint of the next step, y prime xi plus 1. The first derivative is evaluated at the midpoint using the central difference formula. The right-hand side, the differential equation, is also evaluated at the midpoint. In practice, the discretization equation is applied as follows. The advantages of the midpoint method are: it is simple and easy to program. It can be employed for both linear and nonlinear IVPs. The global error for the midpoint method is second order. It is comparable to the trapezoidal rule in terms of cost. The disadvantage of the midpoint method is it requires 2 function evaluations per step, i.e., its computational cost is about twice as much as that of the explicit Euler method. The modified Euler's method is based on the trapezoidal rule. To make the method an explicit scheme, the current estimate yi plus 1 on the right-hand side of the trapezoidal rule is replaced by the explicit Euler approximation. Then we express this as follows. The advantages and disadvantages of the method are practically the same as those of the midpoint method. Let us consider the following first-order initial value problem. We wish to use the trapezoidal rule to solve the given IVP up to x equals 1 and obtain solutions for h equals 0.1 and 0.05 and compare the estimates with the given true solution. We start with the given first-order ordinary differential equation and apply the implicit trapezoidal rule. Substituting fxy into the difference equation, we obtain. Since the IVP is linear, we can solve it for the current step estimate as. The initial condition is x0 equals 0 and y0 equals 2. And we can calculate the abscisses from xi equals I times h for i's from 0 to 10 for h equals 0.1. The initial value is placed in the solution table that we will establish. The numerical estimate for the current step is found by applying the recursion equation we derived. Evaluating y1 gives 1.817391. Using this value and evaluating y2 gives 1.665391. Using the estimated value of y2 and evaluating y3 gives 1.536889. We continue this recursive process in the same manner for y4, y5, and so on until x equals 1 is reached. Notice that the true errors are in the order of 10 to the minus 3, with a mean value of 0.0168 for the solution interval. The solution for the midpoint rule is carried out and the numerical estimates and the absolute true errors for the solution interval is provided. Using this method, 2 leads to the average true error proportional to 0.1 squared. Noting that both methods depicted second-order errors, we conclude this session. That is all for now. See you next time with another topic. Bye.